Hello and welcome to the channel. My name is Victor. Recently, I made a cinematic in Unreal Engine based on the Odyssey, featuring music by the progressive rock band Symphony X. Their song The Odyssey is 24 minutes long and it's absolutely incredible. I highly recommend you listen to it. Ever since I first heard it when they released the album back in 2002, I would picture everything that was happening in my head as the music played. There was one part I always loved near the end of the song, a calmer passage right before Ulysses reaches Ithaca. So, when I started learning Unreal, I thought it would be a great idea to make this animation, to learn more about environment creation and cinematics. This video isn't going to be a step-by-step tutorial, it's just a brief overview of how I build the island and how I combine the Unreal renders with the AI-generated ones. In the first part of the video, I'll briefly cover how I gathered the terrain data of the real island of Ithaca in Greece, how I edited that low-res raw data in Gaea to add more detail, and then how I built the landscape in Unreal using the height map, populated it with vegetation, and generated the cliffs, rocks, and so on. In the second part, I'll show you what the original Unreal renders look like and how I simulated the ocean and the waves breaking on the shore, eventually compositing everything together in Nuke. But it's going to be a very brief explanation, as the goal of this video is not to make a step-by-step tutorial. We are now looking at the main Unreal Engine user interface. As you can see on your screen, the scene currently has a very basic placeholder ocean. This is just temporary, as I will later replace it entirely with a highly detailed fluid simulation generated by AI. If I hit play right here in the active viewport, I can move around the scene freely with my character. This allows you to see how some of the physics elements are behaving. For example, if you look closely at the character's cape, it is being actively simulated in real time using Unreal's Chaos Cloth system. Now, it's true and quite obvious that the active frame rate in the viewport isn't very high at the moment, but that is simply because I haven't spent any time optimizing the map for real-time gameplay or performance. The first thing I needed to recreate the island was a terrain height map. I've recreated the northern part of the island of Ithaca, located in western Greece, which is where the ruins of the palace of King Odysseus, or Ulysses, are located. In these side-by-side comparisons between my Unreal render and Google Maps, you can see that I tried to match the island's actual topography as closely as possible. To get the terrain map, I used the Manticorp website. From there, you can select a geographical area and extract the height map, which is a grayscale map representing the elevation and contours of the terrain. If you take this map and import it directly into a dedicated terrain generation software like Gaea, you can immediately see the basic geological structure of the island. However, there is a catch. This type of real-world geographical map usually comes with quite a low resolution and is filled with imperfections, noise, and jagged lines, especially along the coastline. Because of this limitation, the very first thing I had to do was bring the raw height map into Unreal Engine first. Once inside, I used the built-in sculpt brush to manually smooth out the entire shoreline and erase those digital artifacts. Honestly, I chose to do this step in Unreal simply because I found the brush controls and the immediate feedback much more convenient and intuitive than doing it inside Gaea. Once I had a relatively smooth and clean coastline to work with, I exported it and brought it back into Gaea to begin the high-resolution detail pass. For those of you watching this who have a background in compositing, Gaea's node-based interface will look incredibly familiar to you. That is because it uses a procedural node-based system that is conceptually identical to Newt. We can combine different mathematical and natural effects using various masks to isolate the exact areas of the terrain we want to modify. In this specific section of the graph, you can see my hand-painted masks highlighted in red. I use these custom masks to isolate very specific regions like the vertical cliffs or some of the steep coastal ledges. Once isolated, we can apply erosion nodes, thermal weathering, or different types of procedural noise to give the flat terrain a rocky, rugged, and much more realistic character. Once I was completely happy with the overall look and geological features of the terrain, I moved on to the next crucial step, creating the masks for the different materials. To generate these masks procedurally, we can leverage various node types available in Gaea's library. For instance, we have the slope node, which allows us to select areas of the terrain based entirely on their angle of inclination. On screen, you can see how I'm using this node to target and select only the steepest parts of the cliffs. Then, we have other incredibly useful nodes like the flow node. This node is designed to detect the natural areas where rainwater would erode the terrain over time, essentially mapping out the runoff channels, sediment flows, and crevices that form on the mountainsides. By combining these nodes, I kept creating different complex masks, sometimes blending them together with math nodes. Once the network was finished, I exported all these masks individually so I could plug them into my landscape material inside Unreal. Back inside the Unreal Engine project, the first step is to import the final, eroded height map to generate our actual landscape actor. In this specific case, because the map was so large, I decided to split the landscape of the northern part of the island into two completely separate blocks. I did this because I wanted to pack as much texture density and detail as possible into the prominent cliff areas. Therefore, that specific cliff block has its own dedicated 4K resolution map, while the rest of the island, which covers a much larger and flatter geographical area, uses another separate 4K map. The entire landscape is built to a 1:1 scale. In this case, the total terrain span is about 4 kilometers long from end to end. You might notice a bit of an angled seam or gap where the two terrains meet, but you don't need to worry about that at all. Once the ocean is placed in the level, that seam will be completely submerged and hidden from the camera's view. With both landscape blocks loaded and aligned, I applied a master landscape material that I acquired from the Fab Marketplace. These advanced auto materials come pre-configured so that when you connect your custom masks, they automatically generate detailed surface elements like grass, loose rocks, pebbles, and dirt. When you apply this master material in Unreal, the engine reads all its internal material layers. Your job is simply to assign each of the masks we exported from Gaea to its corresponding material layer slot. To give you an idea, we have one specific mask dedicated to the sandy seabed, another mask for the grassy plateaus and vegetation zones, another one for the steep rock and cliff faces, and a final one to define the areas of dry, loose dirt. Here you can see how the terrain looks with the base materials already integrated across both parts of the map. On top of this base, I added a very simple ocean which, as I mentioned earlier, has no wave or foam simulation, since this is the element I'll be replacing later with artificial intelligence. For the cliffs, I manually placed several rock assets that I also found on Fab and Quixel Megascans all along the coastline. I also added some secondary islands in the background that appeared on Google Maps. You can see that in the distance, there are a couple of islands visible on the horizon. For the loose, fallen rocks scattered around the cliffs, I used an awesome Unreal plugin called Rescatter. This tool is a lifesaver because it allows you to paint and spawn physics-enabled rocks directly onto the slope, letting them roll and settle naturally, which distributes them in an incredibly realistic way. For the dense vegetation, I relied on Unreal's procedural system, PCG, which stands for Procedural Content Generation. The basic workflow here is actually quite straightforward. The PCG graph reads the coordinate points on the landscape surface. Then, through various analytical filters, we can isolate those points based on slope, height, or layer density to define exactly where we want the trees and plants to grow. Finally, using a static mesh spawner node, we instruct the system on which specific types of trees, wild shrubs, or flowers from our asset library should be spawned on those filter points. I also generated the houses using a PCG system, and in this case, I looked for a very basic design mimicking the mud brick and adobe constructions of the era. For the lighting, I used the Ultra Dynamic Sky plugin, which works wonderfully and lets you configure any weather condition. For example, you can adjust the sun's position to whatever height you want or change the cloud density dynamically. Additionally, I use the ultra volumetric system to generate that thick, moody volumetric fog you see floating in the foreground, which reacts beautifully to light. You can see, for example, how the silhouettes of the horse and Ulysses cast gorgeous, dramatic volumetric light shafts and god rays through the mist. Now, moving on to the second part of the video, I want to show you the direct comparisons between the raw, unedited Unreal render and the final polished composite inside Nuke. For the very first shot, I decided to use the LTX 2.3 video generation model inside ComfyUI to create a realistic moving ocean. To prep this, I first rendered out a depth pass and a line art pass of the camera movement from Unreal. These passes were then used as ControlNet inputs inside ComfyUI. This is a crucial step because it allows us to guide the AI model, forcing it to respect and match the exact camera tracking and panning speed of our original 3D render. Additionally, I needed to provide the first frame as a reference for how the ocean should look, which I did using Nano Banana Pro. I simply took a screenshot of the first frame and ran it through Nano Banana to generate a realistic ocean with waves, foam, and everything. You then use that first frame alongside the control net, the depth pass, and the line pass, and those were the only elements I needed for this shot. In the prompt, I described the type of ocean, waves, and simulation I wanted in detail. Basically, the LTX workflow consists of feeding it that initial reference image along with the depth map so it animates the shot while maintaining the camera tracking. This workflow is done in two steps. First, we generate the animation at medium resolution, and in the second step, we run an upscale to recover the original resolution. One important detail is that I had to use a temporal upscaler alongside the spatial upscaler because at 24 frames per second, I was getting too many artifacts when the camera panned and rotated. However, by forcing the second sampler pass to output at a smoother 48 frames per second, the temporal coherence vastly improved. It completely solved the artifact issues, resulting in a much cleaner, incredibly stable render. Once I had this beautiful simulation ready, I hopped into Nuke. I imported the LTX Ocean render and began the process of compositing it over the actual 3D environment. In the 3D render, of course, I had hidden the basic water plane so that only the visible rocky seabed remained. To make the integration seamless, alongside my standard depth passes, I also exported a Cryptomatte pass from Unreal. This allowed me to instantly pull perfect aliased masks for all the individual rock assets and character elements. I also made heavy use of a position pass, because it lets you generate highly customizable 3D spherical masks in 2D space. Once I had all these masks dialed in, I simply layer the AI ocean on top of the seabed, followed by another foreground layer containing the horse, Ulysses, and the cliffs. To wrap up the composite, I applied a tiny bit of overall softness, some lens diffusion, and a subtle touch of film grain and vignetting to tie all the elements together and give the shot a highly cinematic, cohesive finish. For the second shot of the sequence, I decided to change my approach slightly. This time, I used the Kling AI model through the Higgs field platform. I had to switch tools because the main challenge with this specific shot was that the camera travels a very long physical distance across the environment. At the time of rendering, I didn't have enough fine control over the progressive reference frames within LTX to prevent the water from drifting or warping over such a long camera path. Fortunately, Kling features a highly advanced video edit mode. This allowed me to simply write a prompt instructing the AI to replace only the ocean area. In my prompt, I asked it to swap out the flat, basic water from the Unreal render with a photorealistic sea, complete with fluid dynamics and crashing foam along the shore. Kling is incredible at this because it generates the new fluid simulation while keeping the rest of the frame completely untouched and locked. This ensures that your camera match and all your background details remain pixel perfect with zero alignment issues. Once the clean simulation was finished, I followed the exact same workflow as before. I brought the footage into Nuke, pulled my clean masks using the Cryptomatte and the position pass, and composited that gorgeous AI-generated ocean over our Unreal base. And that is pretty much a broad, high-level overview of how I developed and structured this animation. It was a ton of fun building the island's complex geography and finding creative ways to integrate AI generation tools directly into an established Unreal and Nuke pipeline. Well, that is all for today's video. I really hope you enjoyed this look behind the scenes. My plan is to keep experimenting, creating more cinematic animations that combine the power of Unreal Engine with cutting-edge AI, and I'll be uploading these progress videos to the channel from time to time. Thank you so much for watching, and I'll see you in the next one.